Module 1, Fundamentals of Civil Engineering Materials. 1. Introduction to Civil Engineering Materials. Welcome to our course on Civil Engineering Materials. Over the next 2 modules, we will take a deep and thorough journey into the world of materials used to build the infrastructure that defines modern life, from skyscrapers to highways, from bridges to water treatment plants. Civil engineering materials are not just physical substances, they are the backbone of safe, sustainable, and long-lasting construction. The choice of material influences the cost, durability, maintenance, and even environmental footprint of a structure. We will start by understanding what these materials are, how they are classified, and the key properties that make them suitable or unsuitable for specific applications. Our goal is not simply to list materials, but to understand how they behave under different conditions and why engineers choose one over another. 2. Classification of civil engineering materials. Broadly, materials used in civil engineering can be grouped into metals, primarily steel and aluminum, valued for strength and ductility. Ceramics, such as bricks, tiles, and glass, strong but brittle. Polymers, plastics, resins, and synthetic rubbers, lightweight and resistant to corrosion. Composites, combinations of 2 or more materials, such as reinforced concrete or fiber-reinforced polymers. Natural materials, timber, stone, clay, and soil. Each group brings unique mechanical, thermal, and chemical characteristics. Real-world example. For a pedestrian bridge in a humid coastal town, an engineer might choose fiber-reinforced polymer decking instead of timber, because timber would require frequent maintenance due to moisture and termite exposure. 3. Key material properties. Before diving into individual materials, we must understand the key properties that determine their performance. Strength, ability to resist forces without failure. Elasticity, ability to return to original shape after deformation. Plasticity, capacity to permanently deform without breaking. Hardness, resistance to surface indentation or scratching. Toughness, ability to absorb energy and resist fracture. Durability, ability to withstand weathering, chemical attack, and wear over time. Workability, ease of shaping, cutting, or forming. Density, weight per unit volume, affects structural load. Example. Concrete has high compressive strength but low tensile strength, which is why it is often reinforced with steel. 4. Stone as a civil engineering material. Stone is one of the oldest building materials in human history. It is still used for retaining walls, pavements, and as aggregate in concrete. Types of stone commonly used. Granite, extremely hard, resistant to abrasion. Limestone, easier to shape, but less resistant to acid. Sandstone, good for decorative use. Marble, valued for aesthetics, but expensive. Advantages. High durability. Natural beauty. Low maintenance. Limitations. Heavy weight increases transportation cost. Brittle under tension. Example. The Brooklyn Bridge's towers are faced with granite, which has withstood over a century of exposure to weather and pollution. 5. Timber. Timber remains a key material for formwork, scaffolding, and in some regions, structural framing. Properties. Lightweight compared to metals. Good tensile and compressive strength along the grain. Renewable when sourced sustainably. Defect and durability. Vulnerable to termites, rot, and moisture. Strength depends on knots, grain direction, and seasoning. Example. In earthquake-prone Japan, traditional timber pagodas have survived for centuries because of flexible joinery techniques that dissipate seismic energy. 6. Brick and masonry units. Brickwork has been used since ancient Mesopotamia. Today, we have burnt clay bricks, concrete blocks, fly ash bricks. Advantages. High compressive strength. Fire resistance. Good thermal mass. Limitations. Labor-intensive installation. Brittle under seismic loads. Example. The Great Wall of China incorporates bricks in some sections that have lasted for hundreds of years, a testament to masonry durability when maintained. 7. Cement and concrete. Concrete is the most widely used construction material on Earth. Cement types. Ordinary Portland cement, OPC, general purpose. Rapid hardening cement, faster setting. Sulfate-resistant cement, for environments with aggressive chemicals. Concrete variants. Reinforced concrete, steel bars embedded for tensile strength. Prestressed concrete, tension steel cables for greater load capacity. Lightweight concrete, using lightweight aggregates to reduce dead load. High-performance concrete, designed for exceptional strength and durability. Advantages. Moldable into any shape before hardening. Excellent compressive strength. Long lifespan. Limitations. Cracks under tensile stress unless reinforced. Carbon-intensive production. Example. The Burj Khalifa used a high-performance concrete mix capable of withstanding extreme heat and wind loads. 8. Steel in civil engineering. Steel is the workhorse of modern structural engineering. Key advantages. High tensile and compressive strength. Uniform properties. Prefabrication possibilities. Common uses. Structural frames for buildings. Reinforcement in concrete. Bridges, towers, pipelines. Corrosion protection. Galvanizing, zinc coating. Painting. Weathering steel alloys. Example. The Golden Gate Bridge relies on structural steel cables that have been maintained through regular painting to prevent rust. 9. Glass and plastics. Glass. Used for windows, facades, and skylights. Can be tempered, laminated, or insulated. Plastics. PVC for pipes. Polycarbonate for impact-resistant glazing. Lightweight and corrosion-resistant. Example. Modern stadium roofs often use ETFE, a transparent polymer that is lighter than glass yet strong enough to handle wind and snow loads. 10. Composites. Composite materials combine the benefits of multiple components. Fiber-reinforced plastics, lightweight and corrosion-resistant. Reinforced concrete, steel's tensile strength plus concrete's compressive strength. Carbon fiber composites, used in retrofitting bridges and seismic strengthening. 11. Sustainability in material selection. Modern civil engineers must think about embodied energy, total energy used to produce a material. Recyclability, end-of-life reuse potential. Environmental impact, emissions, toxicity, habitat disruption. Example. Using recycled steel can cut energy use by more than half compared to producing new steel from iron ore. 12. Summary of Module 1. In this first module, we have explored the classification of materials, the essential properties that define their performance, detailed overviews of stone, timber, brick, concrete, steel, glass, plastics, and composites. The importance of sustainability in modern material selection. In Module 2, we will move into testing, performance evaluation, deterioration mechanisms, and practical applications in civil engineering projects.